So welcome back to the 11th lecture on the R lecture series. And now we begin with a bit of advanced R. And if you remember in the lecture 1, I had told you that R has very strong graphics, right? So R has extensive libraries that can produce quality graphics and visualization. So today we'll talk about R graphics, and we'll talk about the latest of the R graphic libraries, that is ggplot2, or the grammar of graphics. So today we'll talk about ggplot2, or the grammar of graphics. So the GG in ggplot2 stands for grammar of graphics. The ggplot2 package was developed by Vipin, and today it is basically the gold standard for publication quality graphs. It is now the de facto standard data visualization package in R. It does not come with base R. It has to be, the libraries have to be installed before you can start using it. So you know how to install a library. You can say install.packages, and in round brackets you say ggplot2. And then, of course, when you want to invoke ggplot into your program, you say library and in brackets again ggplot. So we'll see this as we go along. ggplot2 offers a powerful graphics language for creating elegant publication quality graphs, and it is today the gold standard for graphics. So ggplot2 allows you to create graphs that represent both univariate and multivariate numerical and categorical data. So let's have a look at the main features of ggplot2, and then of course we move on to do a practical demonstration of how ggplot can be used to make your graph more informative and more elegant. So there are 5 key steps in plotting a graph in ggplot2. First, of course, you need to tell ggplot what is the data and define your x and y axis. Next, we add the labels. Labels would be your x-axis label, what is being plotted on the x-axis, likewise the y-axis label, and then of course the title of the graph, which is to suggest what is being plotted in the graph overall, right? Then you can choose the theme. The theme could be default, it could be black and white, or it could be colored. You have a wide choices of color that you can use here. Then you could also group your data into certain categorical variables, and all the data in one categorical variable can be plotted together. So this is known as faceting. And then finally, of course, you can choose the geometry or the type of plot that you want to make. And there are a whole lot of plots that are available. You could do a bar plot, a box plot, a violin plot, and so on and so forth. In the example that I show you now, and this will be a basic example, we'll do a bar plot. So now let's also have a look at the data that we have at hand so that we understand what exactly is getting plotted. So we are looking at Arabidopsis genome, and Arabidopsis genome has 5 chromosomes, and the cytosine in Arabidopsis can be methylated in 3 different conditions or 3 different contexts. So you have the CG context where a cytosine is next to a guanine. You could also have a cytosine methylated in the CHG context and CHH context, where H is any nucleotide except guanine, right? So we have this data from the tier 10 where we know the individual positions of each of the cytosine in the CG, CHG, and CHH context, and that is exactly what we're going to plot today. So we have 2 categorical variables, the chromosome number 1, 2, 3, 4, 5. Then we also have the context CG, CHG, or CHH, and then we have 1 numerical variable, that is the number of cytosines in each of these 3 contexts in each of these chromosomes, right? And the objective here is to draw a bar plot to depict this data. So this is the data set that we have. So there are 5 chromosomes, 3 contexts, and then we have the count of the number of cytosines in each context on each chromosome, right? So therefore you have a data of 4 columns and 15 observations, right? So therefore you have a data of 4 columns and 15 rows. So here is our data set. The data set is basically the total number of cytosines in CG, CHG, and CHH context in Arabidopsis thaliana tier 10, and this is basically distributed chromosome wise. So you have 1 categorical variable that is chromosome, you have another categorical variable that is context, and then you have a numerical variable that is the count, and then this is the count in millions, that is the count divided by 10 to the power 6, right? So let's now see how we can plot this data and extract maximum information out of the visual graph that we make. So now we move on to R Studio and start our actual exercise. All right, so we are in R Studio. This is the scripting area, and in my case, I have the console on the right-hand side. And by default, it is here, but I've changed the settings. So I have the console here, And then, of course, this is my environment variable area, and this is the area. The fourth quadrant is where the plots will be visible to us. So I'm already on the plots tab here, so that whenever we do a plotting using the command line here, you should be able to see the plot directly here, right? So let's get started. First, of course, you need to load the libraries. There are two libraries we're going to use here. First is ggplot2, and then the second library that we're going to use here is data.table to read the data, which is in a CSV file, right? So in case you're using ggplot2 for the first time, it may not be installed in your systems. In that case, you need to install ggplot2 first. To install it, you can go to packages here, and in packages, you can go to install, and in install, you can write ggplot2. So it will automatically prompt you here. So you can select ggplot2 and say install. It should ideally get easily installed, right? Likewise, you can install data.table library. And then, of course, you can, to invoke these libraries into your program, you write library ggplot2 and library data.table. So let me just execute this part so that these libraries are loaded into my script now. So I say run, and you have the libraries loaded here, right? Next, of course, you're going to read the data, and the data, for reading the data, I use the fread function, right? So this is my fread function here. I say methylated underscore C, since the data is about cytosines that can be potentially methylated in CG, CHG, and CHH context. I use a descriptive variable called methylated underscore C to represent the data, and this is equal to fread, and in round brackets I give the path to the file. In my case, it is in F directory, R workshop folder, and the file name is rworkshop.csv. A comma separated file is what we have here. And I also specify that the header is true and the separator is comma, because this is a CSV file, right? So I can check the attributes of my data here. I can say capital V view methylated C. This will open my data in a new tab. So I run it here, and you have a new tab where you can see your methylated C. This is the data that I've shown you in the PowerPoint. You have 4 columns: chromosome, context, count, and count in millions. And chromosomes are 5, 1, 2, 3, 4, 5. And then for the next context again, 1 to 5. And for the third context again, 1 to 5. The context are 3. This is your categorical variable. There are 3 categorical variables here. CG is one context, CHG is another context, and CHH is the third context. And then, of course, these are numerical variables. So you have the count, and count in millions is basically the count divided by 10 power 6, right? And you can see methylated C is 15 observations of 4 variables. All right. So then, of course, if you want to further see the summary of your data or structure of your data, you can use this command. So structure methylated underscore C will give you the broad structure of your data here. So it says it is a data.table and data.frame, 15 observations of 4 variables, and then it gives you the a bit more details of what is there in each. Then you could do summary of the methylated C. So this will give you a column-wise summary of the data in your table. So here you are. If you see, this is your first column is chromosome. The length is 15. Class is character. Second column is context. The length is 15. The class is character. Then, of course, the third column is count, and you have the, because this is numerical vector, you have the minimum, the maximum, the first and third quartile, the median, and the mean. And likewise for the fourth column, right? And then you could also check for whether there is an NA value in your data or not. So you can say is.NA methylated underscore C. And when you run this, you see it is false all across. So there are no NA values in our data for now, right? So we can use this directly for making the graph. So now we come to plotting the graph. And first what we'll do is we'll set up the base, which is basically the frame of your graph. That is the x-axis, what is the value on the x-axis, what is the value on the y-axis, the label of x-axis, the y-axis, and the title of the graph is what we're going to first make. So I say graph is equal to, so the variable name I give, the object name I give is graph, and this is equated to, and then I use the function ggplot, because that is going to then allow for reading the data and also defining your x and y axis and the labels. So I say ggplot, and in round brackets, first the object name, that is methylated underscore C, which contains the data. Then I define the aesthetics. In aesthetics, I define that the x-axis is basically going to represent chromosome. y-axis is going to represent count in millions. And then with the plus sign, I add the labels. Labels will be added with LABS. And then in round brackets again, I say X equals to chromosomes, Y equals to cytosine count in millions, and title equals to cytosine distribution in Italia. And these are all separated by commas, as you can see here. So this is my base graph, and then I print my base graph so that I know that everything is fine. And the only thing that is left now to plot is the actual type of geometry or the type of graph that I want to plot. Let me run this part now, and here you are. Right? This is your graph, right? So if you see here, cytosine distribution in Arabia versus Italiana is the central title. This is your x-axis, the chromosomes, and this is the y-axis, cytosine count in millions. Now we make our first graph, and the first graph we're directly going to define what type of geometry we want in a graph. So in this case, we are going to plot a bar chart. So I say graph 1 equals to graph. So all that is included in graph, which is the base graph, will be there. On top of that, I say plus geom underscore call. And in round brackets, I do not give any arguments. So this will create a bar graph. So let's see how this works out. So here you are. This is the graph that you get now. If you see here, these are your chromosomes on the x-axis, 1, 2, 3, 4, 5. And this is the total cytosine count on all the three contexts that is plotted here. So if you see, our graph does not have enough depth because we still are not showing anything about the context that is there for each of these cytosines that are potentially methylatable, right? So let's now add the context to it. So in the next graph, what we do is we make a new graph that is graph 2, and graph 2 equals to graph 1. So everything that is there in graph 1 will be here. Plus, I say in the aesthetics, I say that the color that you're filling up should be representative of the context in which the cytosines are present, right? So I say AES or aesthetics equals to fill equals to context, right? And then I say print graph 2. So this will now print a graph, which will be again a bar graph. And in this individual bars, you'll also have a color distribution based on the context in which each of the cytosines is present. So you run it here. So now in this case, you also have the context defined here based on the color coding that you have. So this light pink is for CG, the light green is for CHG, and the light blue is for CHH. So now you have adequate depth in the graph, and all the data that you have is now finally represented in the graph. Now we can make some small changes into the graph now. For example, let's say I want each of these contexts to be individually represented as a column here. So what I'll do is I'll make a new graph. This is graph 3, which will be containing the base graph, which is graph, which was just the defining of axis and the titles. Then we would say geom underscore call. Again, this is a column graph or bar graph. And in the arguments, I would say position equals to dot. And of course, the aesthetics has to be filled by the context, right? And now when you print the graph, you will have your, instead of the 5 bars, you'll have now 15 bars, and each bar will represent one context. So let me run this now to show you how this works out. All right, so here you are, and now you can see you have individual bars for each of the context. And for chromosome 1, they're all clubbed together. For chromosome 2 again, for chromosome 3, 4, and 5. And very clearly, most of the cytosines are in CHH context, right? And as you can see, the maximum number of cytosines that are in the possibly methylable are in the CHH context. The number of cytosines that can be methylated in CG and CG context are approximately similar, although of course for each of the given chromosomes, there is a little more number of cytosines in CHG context as compared to in CG context, right? And that is also because H can be anything but guanine, right? Then we move on, and we could do a further modification of the graph, and we could basically club them together as per the context. So all CG context chromosome-wise would come into one group, all the CHG context will come into the second group, and all the CHH context will come in a third group. So how do we do that? So for that, what we do is simple. We say graph 4 equals to graph 3. So everything in graph 3 will be carried forward, except that now you are grouping the plots, the columns with respect to the context. So I say graph 4 equals to graph 3 plus facet underscore grid, and then using a round bracket and tilde sign, I say context. And when you print this graph, this is what you get. Let me increase the width so that we have more clarity. So now if you see, you have all the CG values in one block. So all the cytosines in different chromosomes that are metallitable in the CG context in one graph. Likewise, all cytosines in CG context in another block, and all cytosines in CHH context in the third graph, and the distribution is still chromosome wise. So you don't lose any information, just that the grouping is slightly different from the previous graph here, right? So then you could also change the color. If you're not liking the colors that have come by default, you could change the colors, you could define. So I say graph 5 equals to graph 4. So the original graph is what you have, plus a scale underscore fill underscore manual. And in this, I give a vector which is values and contains the colors that I want them to plot. So the first, the CG context will be in brown color, the CHG context will be in blue color, and the CHH context will be in red color. So, and then you can print the graph again. So when you run this out, the same graph, only that the colors are going to change, and accordingly the index is also going to change here. So you say run again, and you have the same graph with a slightly different index. So here you are, this is your graph again, the same graph, just that the colors have changed now, right? And then of course, if you move on, and we could also change the background if you want. So you could say graph 5 plus theme underscore black and white, base size equals to 9 plus theme, panel dot background equals to element underscore rectangle, fill equals to light blue. So these are some of the options that you can exercise to change the look and appearance of graph. So now your background has changed. So these are some of the things that you can do with ggplot, and that would basically give you an idea of how ggplot can be used to make any type of graph. And there are a lot of geometries that are available, and that can be used to visualize your data the best possible manner possible, right? So thank you very much.